Hello, we are the Charging Eagles. We are the electrical vehicle design, build, and test. We are the mechanical team. First, I'm going to be presenting the team members. First, we have Luis Arias. He's the mechanical and system integration lead. Then myself, I'm the CSE mount and cover strategist and designer. Then we have Hyung Kim. He's the manufacturing engineer. Um, we also have Frederick Jimenez. He's the BMS mounting and wiring engineer. Following, we have Sergio Jimenez-Ceron. He's the module mounting strategist. Also, we have Elias Perales. He's the fuse curves engineer. And Ruben Ybarra. He's our BAU structure design.
The Battery Workforce Challenge is a 3-year competition project in which teams will design, build, and test their high-voltage battery pack for Stellantis Ram ProMaster Electric Utility Van. The objective of this project is for the team to design, build, optimize, and test the mechanical structure of the enclosure for the HVBS of the electric vehicle. Through this project, teams will follow regulations given by Stellantis, along with other safety requirements that will be needed as well. So for our problem is everyone that's part of the competition will be trained to be the next generation of engineers and vocational specialists in EV battery technology. So here we will gain hands-on engineering and manufacturing skills, be able to develop our battery testing expertise, practice cross-disciplinary collaboration, and we will design, build, test, and integrate our battery pack for the Stellantis ProMaster EV van. So for our objective for the mechanical team, the battery structure was provided by Stellantis, and so we are given that, and we are made with the task to design and integrate all the components that are within that battery structure. Now, within that battery structure, we will be designing and integrating everything together and making sure everything will work with the rest of the vehicle systems, and those include the module mount solution, the battery disconnect unit structure, electrical connections, the cell sensing unit, and the battery management system.
Hello, my name is Luis, and I'll be going over the competition requirements. So here is a table of the competition requirements that we must focus on the meeting. So our main requirements that we're focused is the operating voltage window, which is to be between 260 to 450 volts. Our next important requirement is the installed battery energy, which is 62 kilowatt hour. And then also our continuous discharge rate of 1C rate. This will allow us to focus on how to size up our bus bars. And lastly, our battery installed weight, which has to be below 625 kilograms.
Here we compare our module's design specifications to the required targets. We evaluated factors such as weight, maximum voltage, module count, dielectric strengths, and the cell configuration. As you can see, the design meets all requirements except weight, coming in slightly above the 70-pound limit at 74.5 pounds. However, all other specifications, including voltage, structural layout, and electrical safety requirements were successfully achieved, confirming that the module design is largely compliant with our original design targets. For our battery module, we selected the Samsung lithium-ion cell. It operates between 3.63 volts nominal and 4.2 volts at maximum charge, which fits well within our module's voltage requirements. The cell also provides a strong discharge capacity, giving us both high energy density and reliable performance. This combination makes it an ideal choice for achieving the power output and efficiency we need in our design. This table shows the 4 module cell configurations we evaluated. Each scenario changes the number of cells in series and in parallel, which directly affects voltage, capacity, weight, and the physical dimensions of the module. Scenarios 1 and 2 use 13 cells in series, giving a higher maximum voltage of 54.6 volts. but they also require more total cells and result in heavier modules. Scenario 3 reduces the series count to 12 cells with 31 cells in parallel, which brings the maximum voltage to 50.4 volts, still within our requirement while improving efficiency and lowering total weight. Scenario 4 is slightly lighter, but sacrifices capacity, making Scenario 3 the best balance overall. It meets voltage requirements, maximizes capacity, and keeps both weight and dimensions within a practical range for our design. This table expands the earlier module level results to the full pack level, comparing how each configuration performs when scaled across all 8 modules. Scenarios 1 and 2 maintain high series counts, gives maximum voltages around 436 volts and large total cell counts. While they deliver the highest overall energy, they also come with significantly higher pack weight, reaching nearly 246 kilograms. Scenario 3 again offers the best balance with 96 cells in series and 31 in parallel per module. It reduces the total cell count and weight while still providing a strong nominal voltage of about 348 volts and 155 amp hours of pack capacity. Its nominal energy of 54 kilowatt hours is comfortably within our target range while keeping the pack lighter and more efficient. Scenario 4 is the lightest option but also gives the lowest capacity and energy. Overall, Scenario 3 provides the best combination of voltage, capacity, weight, and energy density at the pack level, making it the most optimal choice for our final design.
And now we'll be discussing the module design. So here's the diagram of how the current flows through our module. So we have the top bus bar, which is the positive terminal, and the bottom one as the negative. And we see how the current flows through each bus bar. And so with this diagram, we can see which is the cross-sectional area that we need to focus on when conducting the bus bar siting study. It is very crucial to know which thickness to use so that it could handle the current and heat. So here we plotted a graph of current over cross-sectional area given a table by the competition organizers. And we could use this to calculate the thickness of our bus bars based our inputted width and at 155 amps, which is rated for 1C. This is representing the thickness for steady state. So in our case, with the input width of 12 millimeters, we get a thickness of 2.72 millimeters. Now we do also want to check to see what's the minimum thickness using the cell calibration table. These data allow us to see what are the cell limited discharge rates for each cell at different temperatures and different state of charge. And we see that 15 is the highest. So we use this for worst case scenario to determine what's the minimum safe cross-sectional area for bus bars. So in order to determine the cross-sectional area for each cell calibration table, we have 2 seconds, 10 seconds, 30, and 180 seconds. And we got the maximum maximum discharge current, which is the 15 for 2 and 10 seconds, 13 for 30, and 10 for 180. And we can use the IEC adiabatic short circuit equation to calculate our minimum cross-sectional area for each. So now in order to determine our final bus bar design, which is the table on your right, we can compare with our final parameters, which is using a width of 12 and thickness of 3.175 millimeters to get it off the shelf in the market. And that gives us a cross-sectional area of 38.1, which is capable of a rated current of 165 amps, which is above the 1C rate. Thus, this dimension will be useful and proper for our battery design. So this is our last year's module design, where it includes an aluminum enclosure with 13 cells in series and 32 in parallel. And this design consisted of 2 modules and 1 enclosure. In this design, all the components are mounted inside the module enclosure. However, our purpose for this year's goal is also to improve this design. So here's our progression of our module design. We started, instead of having two in one enclosure, we had individual modules. And they're all going to be made out of plastic to make sure our modules are insulated. And in the beginning, we started with these bus bars that are bent outwards. However, this was pretty dangerous since we have conductive components exposed. And so we then implemented a pin and pocket design, but that was also a little bit complicated during assembly in the battery pack. So we then implemented rad-lock pins and connectors that can easily be attached and be attached between module to module connections. Now, ranking the previous design model and our current module design, we rank them based on 6 rating parameters, which is weight, electrical installation, machining time, assembly time, safety, and serviceability. And we see that our current model does have good electrical installation because it's plastic. The machining time is also easy using the CNC. The assembly time is also reasonable. We have less components to assemble. And the safety is very good in our design since we make sure that all conducting components are hidden away. And lastly, our serviceability, we're able to access fuses, all the sense harness to make sure that our module operates fine. So
This
here we
table compares the 4 candidate materials for the module housing: ABS, nylon 12, PA6, and PEEK based on dielectric strengths, melting temperature, density, strength, and cost. While materials like PA6 and especially PEEK offer high strengths and temperature resistance, they also come with higher weight or significantly higher cost. ABS provides a strong balance between performance and affordability. It has adequate dielectric strength, a suitable melting temperature for our operating conditions, low weight, and the lowest cost of the group. Because of that balance, we selected ABS as the material for our module housing.
So here we have a stress analysis of our module from last year's to our current model. And we see that for our current model, we did improve the stresses. So instead of 44 megapascals, we went back down to 3 megapascals using ABS plastic and in our geometry of our model. We did apply 1.5 G as the load represents hard braking on the road. And you see that with our current module design, we have improved the structure aspect of the module to handle these forces. As a result, in our new model, we get very minimum displacement of 0.6 millimeters, whereas the previous module, we had 4.53 millimeters. And lastly, for factor of safety, for our new model, we have 16.25, and our previous one, we had 5.1 due to the lack of structure, which is just, in this case, just a aluminum sheet.
This is our mock-up of our 12-volt battery module built in a 4S5P configuration and housed in an ABS plastic enclosure that we CNC machined based on our final design. The mock-up allowed us to validate the fit, layout, and manufacturability of the housing before constructing the full module. We also performed the electrical isolation test on the enclosure, and it passed with no voltage or current detected on any of the non-conductive ABS surfaces. This confirms that the CNC machine to ABS housing provides the electrical insulation and safety performance required for our system. This slide shows the wire bonding process used in our module mockup. The wire bonds were welded using an ultrasonic welding machine, which allows us to create precise and reliable connections between the cells and the bus bar. The graph on the right displays the deformation and the current profiles during the welds. These curves are consistent and stable, which indicates that the weld parameters are weld controlled. A steady deformation curve means the bus bar is bonding uniformly, and the stable current levels result in stronger, more repeatable welds. This data confirms that our wire bonding process produces high-quality connections suitable for our battery module.
We will now go over the module mount design. The module mount design and its first revision were meant originally just to hold the battery module into place. Now, I went over in SolidWorks, I did some measurements from the battery pack, and I came to a conclusion just to make a simplified rectangular shape to then hold the battery module with screws that will go into the main module plate. And so that was the main objective for this design. For the second revision, I wanted to make it lighter, so I removed some material. And as you can see from the right side, I kind of just made indents to the walls and to the structure to see if that would help reduce weight. Made some hole diameter changes as we are changing the screws to try and find out which would be best to keep this together. And then along with some other body dimension changes as the battery pack fluctuates around, and I was given a little bit more or less area to work with for the mount itself. So for the third revision of the module mount design, the module spacing had changed. They were a little bit farther apart, so that changed my overall dimension. And along with the hollowed out frame, that was put into place into design to reduce the weight that was needed without having to make any fancy indents or anything like that. And it was hollowed out and broken up into different pieces, so 4 pieces as well. So the frame can be changed into an assembly, and then it can also be easily manufactured with this new design as it's not one solid part. It won't be as difficult. So as I was going through those, this is the trade study. I just went with over all of them, and I just kind of looked at the different designs, and it does show that it just got better as we go through with the total score that I came up with. And as we could see, the third design is most likely the better fit as it's just continuing to improve and will be able to do its functional ability, which is to hold the battery module into place.
The battery disconnect unit structure design, or BDU for short, houses the electrical contactors, fuses, and sensing elements that allow us to safely connect and disconnect the vehicle's battery pack from its operating conditions. Some of the several key design constraints we had to meet were to maintain an 11 millimeter clearance from the vehicle's top cover while keeping the BDU in a fixed position that allows the BDU's pack cover shape. The mounting had to align in parallel with the battery modules while considering creepage, clearance, and wire routing. We also required a high-strength enclosure capable of withstanding the driving conditions. To show the initial geometric constraints, the enclosure must fit precisely within the fixed boundaries of the battery pack, maintaining required clearances and matching the top cover's contours. The dimensions and angles shown here are guided how we form the structure so that it aligns with the existing mounting points. So showing these 3 design alternatives, we evaluated for the BDU enclosure. Each of these were shaped by our structural and clearance constraints, and a trade study was done to see what could integrate with the vehicle's battery pack, meeting the required tolerances and withstanding the dynamic loading. While some of the designs offer easier mounting and strong vertical forces, they also brought weaknesses under multi-directional forces. So these trade-offs helped guide us towards the most robust and practical solution, which is design alternative 3 and leading into design concept 1, which features this large base plate that extends to the existing mounting holes while utilizing all of these bolt holes for stability. The cutouts were intended for the component clearances of the modules, and a rib feature was added to maintain its rigidity and strengthen its structural integrity. The pros of this design were the simplistic integration, its strong resistance to dynamic loading, it meets all its tolerances, and reduces the amount of component interferences. The con of this design would limit the component placement on the outskirts of this design. In design concept 2, the base plate is extended out horizontally to the end of the modules, which is intended to add any mounting for additional electrical components. The pros of this design creates additional space for additional electrical components and maintains alignment while utilizing a lot of surface area. The cons of this design is that larger surface area causes structural stress or is prone to bending. In design concept 3, these added cutouts on these base plates were intended for integration of certain electrical devices, and wire routing cutouts were considered for these cutouts as well. The pros of this design is that wall surroundings were now created as a partial enclosure for protection of these electrical components, and also provides easier accessibility for connecting and wire routing. The cons of this design is that with the larger surface area taken up and these thin area cutouts would cause more structural stress. So conducting a material trait study, we compared several polymer materials based on impact strength, heat resistant, electrical insulation, and structural performance. The materials like polypropylene, polycarbonate, and ABS offer useful properties. However, nylon stood out as the most suitable as its high mechanical strength, stiffness, and wear resistance, and contained reliable performance. So analyzing the BDU as a bending beam analysis with fixed ends and a distributed load, we can obtain a spring constant, which is the force divided by deflection. From that, we can obtain a natural frequency, which is the square root of the spring constant divided by the mass of the system, and convert that frequency to hertz by multiplying that value by 1 divided by 2 pi. So analyzing the stress analysis, theoretically, the BDU structure is simplified into a bending beam equation with fixed ends and a uniform distributed load. This simplified model provides an estimate of the deflection, spring constant, and natural frequencies that the enclosure can experience. Looking and analyzing the stress analysis in SOLIDWORKS simulations, the BDU structure is analyzed at the center of the box region to replicate the bending beam analysis under its distributed load. The simulation considers the structures and characteristics based off of its full 3D model and idealized constraints, but it can help predict its behavior under the loading conditions.
The component that I was tasked with mounting, it's the CSC. We are seeing it on the screen. It's a cell sensing circuit. It can monitor up to 16 cells. It has 2 paths for communication, but we will be focusing on ISOSPI. The CSC is designed to monitor the temperature and the voltage that each cell is receiving. So in case that we have one volatile one, we will get the numbers. Then it's used to test battery systems safely and accurately, and can be used in large battery stacks like the one that we will be building. So how does it work? The way that it works, it monitors with 2 twisted cables, and it measures the differences between those 2 signals that it's receiving. It's not working with electricity, it's just working with pulses. So this was my first mounting and enclosure solution. It was very quickly discarded because it didn't fit the requirements. And it also was really hard to work with it. For my second design, I just made this cover where we would slide the CSC in those sleeves that you can see. But unfortunately, the cables and extra connections weren't accessible in this design, so I had to scratch data. Then design number 3, more simple, just a couple of spacers and fasteners to hold everything in place. And then finally, design number 4, it's an enclosure for the CSC and the components surrounding it. Here I don't have the photos of the extra components that this enclosure will be housing, but it's I have the CSC just to give an idea what it will look like. Lastly, I will be presenting a design trade study for all for my designs. I combined the cover with the rest of my designs because the first two were covers and mount solutions. So I think it just made sense. For the first and second one, we can see that they got really low scores comparing them with the spacers and the fasteners, and then with the cover with all for all the components. Um, they got the highest grade scoring. So um, I will be going with those two designs.
The battery management system, or BMS for short, is a device that regulates and monitors the temperature, voltage, current, health, and the charging status for the entire battery cell pack. That also includes the individual battery cells within it. And for my mount design, um, um, I I designed two different mount designs for two separate BMSs. One called the M130, and another one called the M450. Both of them proved challenging to design due to um, not being any available space in the battery pack module itself. So I had to find a workaround to find any available space to place the two BMSs in the battery pack module. And these two had the difficulties with um, mounting, where for the M450, the blue one, it has three screw holes at the bottom of the device itself, and I had trouble trying to find how to mount it on a plate and mount it on the battery pack assembly. But then I figured out that it would be easier um if I had seven screw holes, three to connect the plate to the M450, and four screw holes that will connect the mount itself to the battery pack assembly. And I was able to find space for that in the middle, right near the BDU. For the M130, that proved a lot more challenging because it was due to its size and shape and geometry. Finding any room for it was difficult. I tried putting it everywhere, but I couldn't. But I figured out that I was able to place it on the side of the battery pack assembly itself, the whole thing. And the only reason why I was able to, because it was considered a low voltage device. So I had more freedom to where I could put it place it in the battery pack module itself. So I had it mounted on the side where it would connect to an already existing structure that already had screw holes, which would use the existing uh hole for this one. And on the sides, oh, for the M130, it has holes, but no screw holes. So I had to design it to where I had to design it where I added to add threads, since the M130 had no threads, so I had to add the plate that had threads that would go into the M130 and connect it to the plate itself on the back, as seen in the photo.
So here we did vibration over the summer. This is collecting by real data of vibration on our Ram ProMaster. On the right, we see images of how we use the Observe VR 1000 and the Observe View software to able to record live data of our vibration. So we routed each of the sensors, accelerometers underneath the band and attached it directly on the battery pack to see what are the forces and vibration the battery pack experiences. So on the left, we have a vibration profile of our experimental data in the vertical direction, and then we compare it with the J2380 SAE profile at the 1.5G and the 0.75G. This allows us to see how close our real data is comparable with the SAE test profile, and can use this on the shaker table when we test our modules to ensure that our designs are robust. Thank you. I would like to acknowledge our advisors and professors at CalCLA. I would like to thank Dr. Bachman, Dr. Traverdi, Dr. Wang, Dr. Medina, Professor Ybarra, and Professor Blake for supporting us along the way and giving us this amazing opportunity to learn and grow as a team, and share valuable insights and advice. I also like to thank our Stellantis mentors, Manu and Hyung, for also giving us advice along the way and for helping us through this amazing learning experience. Lastly, I will also want to thank our liaisons from Argonne National Laboratory, which is Ravi and David. They're one of the competition organizers and have been very supportive throughout the years. Lastly, I would also like to thank our sponsors, Stellantis, Argonne National Laboratory, Department of Energy, and HQMD for donating us enough resources so that we could continue with the program. Thank you.
Our last item on the list will be the conclusion, which what we were able to accomplish was that we were able to design and integrate all the initial components that we presented into the Stellantis provided battery pack structure, which includes 8 modules, 4 module mount structures for it, 1 BDU, 2 BMSs, 8 CSEs, 4 cooling plates, and 4 structure foams for the cooling plates. Thank you.